Here's a quadratic equation. Let's talk about solving it. When in algebra you discovered that there were basically two ways that you solve quadratic equations like this. One is by factoring and the other is by using the quadratic formula. We'll look at the formula in just a little bit, but if we want to solve this by factoring, then we factor this polynomial. So here's what we're doing. Now let's talk about the factoring process itself first. We factor into binomial times binomial. We know we identify the first elements of the two binomials by asking ourselves what are the factors of this first item in the trinomial that we're factoring. Well, let's see, it would take x times x to give x squared. So these items will be x's. The last sign here is positive. It means that these two signs are the same. Since the middle sign is negative, these two are both negative. And factors of 6 are probably the 2-3 combination rather than the 6-1 combination here. So we have 3 and 2. And let's verify the middle term. In fact, let's verify all of the terms in the trinomial. We know that this is multiplied to give that. X times x gives x squared. Negative 3 times negative 2 gives 6. The middle term is the combination of this product, the negative 3 times x, negative 3x, and the product of negative 2 times x, negative 2x. Negative 3x with negative 2x, that's negative 5x, and therefore this is a correct factored form. All right, all of that is information you've had before. Now, the solutions to our quadratic equation are the values of x that cause each factor to become 0. And the value of x that causes this factor to be 0 would be 3, and the value of x that causes this factor to be 0 is 2. Now, why are those solutions? Well, they're solutions because they are replacements for x which will make the original statement true. And we can see that in this statement, or we can see it up here. If we replace x with 3, 3 minus 3 makes this 0. 0 times anything over here is going to be 0. 0 equals 0 is a true statement. These are solutions. Now, we call them solutions, and we look for them, we investigate for them by saying, what value of x will cause this factor to become a 0? You see, and so we could call these zeros. This is a 0 for that linear factor. This is a 0 of our polynomial, we could say. Now, I also want you to notice this, that the solutions, or the zeros, also lead us to factors. That is, if x equals 3 is a solution to the equation, then x minus 3 is a factor of that polynomial. 2 is a solution, or a 0. X minus 2 is a factor of that polynomial. And it's using that idea, by the way, is the way that teachers a lot of times will make up tests. If you want your solutions to be, let's say, 5 and 7, then you make a polynomial that is x minus 5 times x minus 7 and set it equal to 0, and you've got a problem to solve. Anyway, the relationship between factors and zeros is what I'm trying to point out here. All right, now, let's concentrate on zeros of polynomials. The zeros lead to solutions to the equation. We don't really need an equation in order to look for zeros of a polynomial. Let's look for the zeros of this polynomial. Now, we're looking for the zeros by using the method of factoring. We could use the method of using the quadratic formula if we wanted to. We'll bump into that in just a little bit. Generally, you try the factoring method first, and if you can't factor very easily, then you go to the quadratic formula. So factoring here, well, let's see, we kind of follow our nose through it as we did before. X times x would give x squared. The last sign is positive, making these two signs the same. The middle sign is negative, so minus, minus. And then factors of 9, probably the 3-3 combination. Verifying the middle term, negative 3 times x, negative 3x, negative 3 times x, negative 3x together, negative 6x for the middle term, therefore a correct factored form. The importance here is that although we have a quadratic expression, we only have one 0. Actually, we have 2, but they are repetitions of one another. We have 2, but they're the same. So we only have one distinct 1. And that would be x equals 3 is our 0. For this one, when our leading coefficient is other than 1, we still kind of follow our nose through it. but it's kind of a fishing expedition here to find the values. Now, to break down 2x squared, it's probably going to be 2x times x for 2x squared. The last sign is negative, so the signs here are different. Now, where do we put the plus sign? Where do we put the minus sign? We could analyze this very carefully, I suppose, and determine where it should be, but really, just take a shot at it. Just make this plus, make this minus, and then pop something in and use the kind of a trial and error method here. Factors of 3, the 3-1 combination. Put 3 here, put 1 here, and let's test. So we have 3x and then minus 1 times 2x. 3x minus 2x would be 1x. Is that the middle term? No. So this is not the right factored form. So we kind of go back to the drawing board and we try another combination. Let's swap the 3 and the 1. Let's put the 1 here and the 3 here and see what happens. We have 1x minus 3 times 2 is minus 6x. Minus 6 plus 1 would be negative 5x. Is this negative 5x? No, we have a difference in sign. So all we need to do is swap the signs and we should be okay. So let's see, if we swap the signs, this will be plus, that'll be minus, and everything ought to be all right. We have 3 times 2x, 6x, minus 1x, that would be 5x, a correct factored form. Now we want the zeros here, so we'd like to know the value of x that will cause each factor to become 0. This one's easy to identify and we could do it by observation, but what about this one? See, it's not so easy to see through this, and when they're not easy to see through, you can just set it up like this. You can say, gee, I'd like to know the value of x that will cause the factor 2x minus 1 to be equal to 0, and then just solve this little rascal. So x is 1/2. So x equals 1/2 is 1 0, and the other 0 is x equals negative 3. On this one, we might try to factor, and we would find that we kind of bump into a brick wall on all of the combinations that we try. So we would use the quadratic formula. Now remember, the formula is x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. And the a, b, and c in the formula come from a, b, and c in our expression. So x equals, and we just replace letters with numbers in the first step. We never go through and try to perform operations. We want to just replace letters with numbers and be safe with the situation. Negative b means negative 6 plus or minus the square root of b squared. Oh, that's 6 squared. Minus 4 times a is 4 times c is 1. All of this is over 2a. That's 2 times 4. X then is, now we go through and perform operations. Negative 6 plus or minus the square root of 6 squared is 36 minus 4 times 4, 16, all over 2 times 4, 8. And then collecting here, let's see, x is negative 6 plus or minus the square root of 36 minus 16, that's 20 over 8. Now 20 is 4 times 5, and so we would rewrite as negative 6 plus or minus the square root of, and think of this as 4 times 5 like this, in order to simplify, and then we can take the square root of the 4. I'm just going to kind of go out to the right because I'm running out of room below, but negative, usually I would write below rather than put these extra equal signs in here, but at any rate, let's see. We have plus or minus 2, the square root of 5 over 8. Now, here we have an interesting cancellation mistake opportunity. This is one of the most often made mistakes in algebra, and it is one where the tendency is to say 2 into 2, 1, 2 into 8, 4. That is, make a cancellation here, and then make another cancellation with the 6 and the other 2 that's in 8. And that's an incorrect assumption. This 8 actually divides both parts of the numerator, and we could show that as a separate step. We could make 2 separate fractions out of this. Or we can factor in the numerator, and that's the safest thing to do. That is, we pull the common factor 2 out, and we have negative 3 plus or minus the square root of 5 over 8. And now the 2 and the 8 can cancel, leaving 4. So our fraction is negative 3 plus or minus the square root of 5 over 4. Now realize that if we're looking for zeros here, that we have actually two of them. The plus value on the square root of 5, the minus value on the square root of 5, each give a separate value for this fraction. And we can approximate that value using a calculator, and I think those approximations turn out to be negative 1.309 and negative 0.191 when you punch the calculator for this. But at any rate, that's the process. All right, let me erase here because I want to come down on this other problem. Now notice the other problem. This next problem says to find the domain. Acceptable replacements for x. What values of x are acceptable when a radical is involved? Well, when we're taking square root, the radicand needs to be positive or 0. So we're trying to find the values of x that will cause that to occur here. Now, the technique for doing that is not readily obvious here how to do that, but what we're really doing in this problem is we're saying, gee, we'd like to find the values of x that will cause the radicand to be greater than or equal to 0. So we're really just solving a quadratic inequality when we're asked to find the domain of this. You see, and I'm making the request for what we're trying to find using the inequality business. You don't absolutely have to write this down, but you have to understand what we're doing, that we're actually thinking about this in going through the process that we're going to go through next, which is factoring. So we factor here, and remember from a previous section that we're doing this in order to find some critical values, and those values are critical because there are the spots on the number line where the sign changes within those factors. But this is x times x for x squared. Last sign is positive, middle sign negative, so minus, minus, and the 2, 1 combination. Now the critical numbers are x equals 2 and x equals 1. These are the zeros of those two factors. Now those are critical values because they are places on the number line where the sign of each of these factors will change. That is, if we're out here with an x value greater than 2, if x is greater than 2 and we subtract 2, then we have a positive value actually for both of these factors. And incidentally, in this interval, therefore, if both of the factors are positive, positive times positive gives a positive result greater than or equal to 0. Yes, that's true. And therefore, in this interval, we have values of x that will cause the radicand to be positive and therefore valid, part of the domain of our expression. Now, when we choose a value that is to the left of 2, just to the left of 2, you see, just smaller than 2, minus 2, negative. You see, negative. Negative times positive is going to be negative, not greater than or equal to 0, and therefore the values in here are not part of the domain. And we're going to find out that when we cross this rascal, the sign of this one will change. That is, if we're over here for values greater than 1, minus 1, positive. Then jump to the other side. Less than 1, minus 1, negative. You see, so the sign changes for that factor, and therefore the dynamics of our expression will change somewhat. We find out that values over here are also part of the domain, but this is not a part of the domain. Well, how do we indicate that? And by the way, what about the critical numbers themselves? You see, 1 and 2 are values that cause the two factors to become 0. It causes this inequality to be, well, true or false. Let's see, if this is 0, or either one of them is 0, then we have 0. Is 0 greater than or equal to 0? Go like this, yes. So therefore, the critical numbers are indeed part of our domain for this expression. Now, we can show that domain like this. We can say then, another way to describe the domain would be an interval notation. This is the interval from negative infinity to 1, and this is the interval from 2 to infinity. And it is the union of these two that will give us our complete domain. Let's talk about some factoring techniques. We talked a little bit about factoring trinomials earlier, but when you studied algebra, you talked about factoring binomials and factoring when you have 4 terms and that kind of thing. If you have 2 terms, you can have 3 situations involved. One of them is the difference of squares. Remember, if you factor the difference of squares, you get the sum of 2 terms times the difference of the same 2 terms. That's basically the idea. And the items that are in the binomials are the values that are squared to give each of these 2. So x is squared to give that, so x appears in these 2 positions. 5 is squared to give 25, so 5 is in each of these 2 positions. So x plus 5 times x minus 5 is the factored form. It turns out that we can also factor the sum of 2 cubes or the difference of 2 cubes, and the strategy is pretty much the same. That is, we factor into a binomial times a trinomial, and we set up the skeleton for that factored form first. We identify the items in the binomial and then the items in the trinomial. The binomial items are identified as simply those items which, when cubed, will give each of these. X is cubed to give x cubed, 5 is cubed to give 125, and the sign here is the same as that sign. So x plus 5. Now we go and identify the items in the trinomial. The first term of the trinomial is this guy squared. The last term of the trinomial is this guy squared. The middle term is the product of these 2 without regard to sign. So 5 times x, 5x. And actually the sign here is the sign opposite that one. There is one minus sign in this entire factored form. If it's here, it's not there. If it's not here, it's going to be there. You see? And that's kind of the way you look at it when you did this in algebra. And I'm running through it quite quickly here, and let's go through it again. This time we have the difference of cubes, and we identify the items in the binomial first. And the items cubed here, well, x is cubed to give this term, 3 is cubed to give that term, the sign minus. Now, the terms over here, first term squared. Last term squared goes here. The product of these 2 without regard to sign, 3 times x, 3x. And it's plus because that's minus, this is going to be plus. And it's 3x. Okay, so a factored form. Now, we're not looking at all of the nuances involved in all of this factoring. One other situation was factoring by grouping, and we face that, or we use that technique when there are 4 terms involved. We might try that technique in this situation. That's not why I put this problem up here, but that would be the first thing we would try. Now, we would find that it's not factorable using grouping. We have to use another technique here. But when you use grouping, here's the idea. You would think of these 2 items as a group and those 2 as a group. Now, there are other grouping possibilities. You can think of this one with that one and then these 2 together, or you can think of this one with that one and then these 2 together. So there are 3 actual combinations for attempting this factoring by grouping, and it turns out that 2 of them will work and 1 of them will not. Now, none of them work in this particular problem, but when it's factorable, 2 of them will work, 1 will not. If we were factoring by grouping, I would take out a common factor, x squared here, and I would be left with x minus 4. Now, in this circumstance, what we're looking for is a situation where we have an x minus 4 factor over here as well, and we can't create that situation here, so that's why this method doesn't work. Okay. Since we know the method of factoring by grouping doesn't work, we need another technique. Now, in this problem, let us suppose that we know 1 0. And there are techniques for discovering a 0 in a circumstance like this. But we'll look at those techniques a little bit later, at least 1 or 2 of them. But suppose we know that 2 is a 0. Now, if x equals 2 is a 0, then that implies that x minus 2 is a factor. And if x minus 2 is a factor, then it means that we can take this polynomial and we can factor it into x minus 2 times some other polynomial. And the trick right now is to find that polynomial. How do we divide x minus 2? See, what we're going to do is divide x minus 2 into that. You see, this is kind of like, it's kind of like saying we have a number like 20 and we know that 4 is a factor of 20. What's the other factor? Well, we say we can find the other factor by just dividing 4 into 20. You see, 4 into 20 is 5. Oh, yeah, 5 is the other factor. You see, it's a trivial example, but it's exactly what we have here. It's the same idea. Now, it's the method of division that I really want to show here, and that method of division is called synthetic division. You learned this probably in algebra, but here's how it goes. Now, we want to divide x minus 2 into that. So synthetically, we divide by the 0. We divide by 2. We set up the synthetic division like this. And we are going to enter here the coefficients and the constant involved in the polynomial into which we're dividing. Now, I want to notice first that we have no terms of missing degree. If we have a missing degree term, like if we didn't have any squared term up here, then we would need a 0 as a placeholder in this division process. So we have 3, 2, 1, and a constant. Okay, that's good. Now, we use our coefficients. Notice I'm leaving a little space between them. And the constant. And away we go. And here's how it works. We bring down the first item, and now we multiply. 2 times 1 is 2. And then we add. Negative 4 with 2 is negative 2. And now we multiply. 2 times negative 2, negative 4. And we add. 5 with negative 4 is 1. And by the way, I know that this is going to go evenly. If 2 is a 0 and x minus 2 is a factor, I know that x minus 2 will divide this evenly. Has to. And I'll know that if I get 0 right here. Let's see. 2 times 1 is 2. 2 with negative 2 is 0. And therefore, I'm verifying what I knew before by looking at that 0. 0 is the remainder in this process. Now, these are the coefficients and the constant involved in a polynomial which belongs here. And I hope that this is a review for you. It should be, because I'm going through it very, very quickly. And by the way, the notion of synthetic division, you know, when we could use polynomial division, by the way. We could divide as a polynomial x minus 2 into that polynomial. And it's kind of a long process, and it involves retaining all of those x's and all of that kind of thing. But synthetic division is just a technique for trading in the more difficult operations of division and subtraction for the simpler operations of multiplication and addition. You notice what we did here in synthetic division. Multiply, add. See, multiply to get the negative, multiply these two to get the negative 4. Add these two to get the 1. Multiply to get the 2. Add to get the 0. You see, multiplication and addition are part of this synthetic division process and not division and subtraction. Okay, at any rate, these are coefficients and constant, so it's 1. Now, notice you identify the degree of the polynomial. There are a couple of ways of doing it. One way, and probably the best way, is to say that this polynomial is going to be 1 degree less than the one that you started with. You see, you're dividing by a linear factor here, so this leftover factor is going to be 1 degree less than that. So it's going to be 1x squared, and then minus 2x, and then plus 1. All right, so this is a technique for factorization. It's also a technique that we can use for other purposes as well. But for factorization here, we're looking for all the zeros here. We are given one of them. One of them gives us a factor. Synthetic division gives us the other factor. And we go through and we factor this trinomial part using the regular method. Let's do that. So we have x minus 2. And then setting up for this part, we have x times x, plus sign here, minus, minus, factors of 1, 1, and 1. So here is the factored form, and our zeros then for our polynomial are x equals 2 and x equals 1. Now notice that we could write this part as x minus 1 squared. A little while ago, I made a comment that you may have questioned. It was a comment something like, suppose we know that a certain value is a 0 of a polynomial. And you may have been thinking, well, how in the world would we know that? Well, it turns out that there are a number of algebraic strategies for identifying the zeros of a polynomial. And I'm going to show you one of them right now. And it just kind of narrows our choices in the investigative process. This one does. It's called the rational zero theorem. Now, zeros can be rational, irrational. They might not even be real numbers. But this theorem allows us to identify the possible rational zeros involved in a polynomial. And those rational zeros are identified as all of the fractions that are composed of the factors of the constant in the numerator and factors of the leading coefficient in the denominator. Now for this one, the constant is 3, the leading coefficient is 2. And the factors of 3 are 1 and 3. Factors of 2 are 1 and 2. Now notice I have plus or minus before each one of these. So it's plus or minus every combination that we can make here. And if we're thinking about the items up here over 1, it's 1 over 1, which is 1. 3 over 1, which is 3. 1 over 2, which is 1/2. 3 over 2 is 3/2. And it's plus or minus each one of those. Now, this gives us a number of items to try. It's 2, 4, 6, 8 possibilities here that we could actually try. And you might think, well, that's an awful lot. But it certainly has narrowed it down from not knowing any possibilities at all to having just 8 items to try. And there are strategies from algebra, and I don't want to get too sidetracked here, but there are strategies to identify intervals in which we may have a zero. And if one of these rational values turns out to fall in that interval, then it would be a great candidate to try as a zero. At any rate, suppose we want to investigate to see if 3 is a zero of this polynomial. It's the same polynomial we had over here. Now, to test to see if 3 is a zero, and we kind of use this idea. If 3 is a zero, then x minus 3 is a factor. And if x minus 3 is a factor, then x minus 3 will divide that polynomial evenly. And to divide x minus 3 into that polynomial, we can divide synthetically by 3. So to see if 3 is a zero, we divide synthetically by 3. And here's how that goes. We have 3. Now I'm looking up here to see if we have any gaps in terms of the exponents. We have an exponent of 3 here, 2, 1, and the constant. So no gaps, and I'm just using therefore the coefficients and the constant. If we had a gap, we'd have to put a 0 in as a placeholder. So we have 2, 3, negative 8, 3. 2, 3, negative 8, 3. Now dividing synthetically, we bring down the 2. 3 times 2, 6. 3 and 6, 9. 3 times 9, 27. 27 with negative 8 is 19. 3 times 19 is a rather big number, and that big number with 3 is also a big value, and that means that our remainder here is not 0. The division goes evenly if the remainder is 0. And the remainder is not 0. This doesn't go evenly, so 3 is not a 0. Let's try another one. Is 1/2 a 0? Well, I want to show this one because I want you to realize that it's okay to divide synthetically by a fraction. And it's really pretty easy. It's 1/2, and we're dividing synthetically into the 2, 3, negative 8, 3 business. Bring down the 2. Half of 2 is 1, 3 and 1, 4. Half of 4, 2. Negative 8 with 2, negative 6. Half of negative 6, negative 3. Oh, happy day, 3 with negative 3 is 0. So our remainder is 0, and therefore 1/2 is a 0. Now, not only that, but 1/2 is a 0, so x minus 1/2 is a factor. And the leftover factor, the information for it, is given right here. That is, we can now take that and we can factor it into x minus 1/2 times, now, we're using these as the coefficients and the constant of a polynomial. The polynomial has a degree 1 less than the polynomial we divided into. That polynomial was of degree 3. So this one is of degree 2. So we have 2x squared plus 4x minus 6. Now let's try to find the other zeros. It should be pretty easy. I see a common factor of 2, so we have x minus 1/2, and then snag the 2 out, and we've got 2 coming out of this term leaves x squared, 2 out of this term leaves 2x, and 2 out of negative 6 leaves negative 3. And now that's pretty easy to factor. I want to show you something here about this 2, this constant 2. Notice what happens if we multiply this 2 into this binomial factor. It'll clear the fraction, you see. And that's often the case when we have a fraction as a 0. So 2 times x minus a half is 2x minus 1. And we're a little more accustomed to seeing binomial factors in this form. And then, well, let's see, factoring this trinomial, x times x for x squared. The factors of 3 are 3 and 1. The last sign is negative, so we have the plus-minus combination, and it turns out to be plus 3 with minus 1. So all of the zeros then are, well, from this one, it is 1/2, as we found earlier. And for this one, x equals negative 3. And for this one, x equals 1. So our 3 zeros of that polynomial.